In this video, we'll talk about obstacle isolation and predictive collision detection. We have three main objectives. First one being the ability to isolate different obstacles rather than simply detecting obstacles. Second, quickly detecting a collision by creating a projected path using the vehicle's dynamics. And last but not least, we want to build a more robust system for failures of the perception devices that are used to detect obstacles. Let's consider a scenario where the vehicle needs to make a decision to avoid a collision. What could be at stake here? There could be a pedestrian in the way, and obviously the cars will be in our way, and so forth. And we definitely want to make the vehicle to make decisions based on the context of the obstacles, rather than blindly avoiding all obstacles the same way. And to do that, we need obstacle isolation, a way to distinguish different obstacles. And we want to address the issue of detecting obstacles that are within a certain view window through the LiDAR sensors, especially when the vehicle is making turns in the intersections. And what if the LiDAR or camera fail while going fully autonomous? We certainly don't want these horrific accidents to happen as was shown below. Our claim is that by isolating different obstacles using both LiDAR and camera, the vehicle can be programmed to prioritize specific objects. And with our collision prediction algorithm, we are able to accurately detect collisions and decrease the collision detection time by up to 13.21 seconds compared to the straight projection model in MP4.
We implemented perception, decision, and control modules. Perception module uses the LiDAR and camera to accurately detect the pedestrian's position. The decision module uses the vehicle's steering angle and velocity, as well as the pedestrian's position, to predict the vehicle's path and if there will be a collision. The control module uses the decision on if there will or won't be a collision to make the vehicle stop or continue moving. In the perception module, we begin by running the camera through a pre-trained YOLO model to detect pedestrians. We then take the pixel coordinates from the bottom of the pedestrian's bounding box and convert them to pixel coordinates for the bird's eye view image by applying a calibrated transformation. At the same time, we process the LiDAR by filtering points in a certain region and then flattening the points to create a bird's eye view image. We then run Haas circles on this bird's eye view image to find all shapes resembling a person. Finally, we use the pedestrian's previously completed bird's eye view pixel coordinates to filter out the wrong Haas circles. This is done to overcome each sensor's weaknesses with another sensor's strengths. In this case, the LiDAR's bird's eye view can confuse pedestrians with similarly shaped objects, whereas the camera can accurately detect pedestrians. Also, the camera can't accurately detect the distance to the pedestrians, whereas the LiDAR can.
Next, to achieve our target, we derive the following algorithms. First, to transform an image pixel to world coordinate, we calibrate camera reference pixel to the corresponding ground point with respect to the vehicle. We then find a transformation matrix, which subsequently map pixels to actual world plane. Then, to make faster safe decision, we must predict vehicle's path. With current position, knowing vehicle physical parameters, we feed them to dynamics function outputting a next waypoint. Through iterative means, we then able to create a set of waypoints and subsequently define a safety region. The algorithm is repeated again once vehicle moves to a new position.
Into our result, the perception module loaded into the vehicle was able to detect all the surrounding obstacles, represented by the white dots in the figure, and isolate pedestrian, represented by the red dots. Subsequently, the vehicle was able to successfully predict upcoming collision with the pedestrian and stop the vehicle when the pedestrian was actually on the track. In addition, it was also able to avoid unnecessary stopping if the pedestrian is near but not on our track. To further emphasize how we've accomplished our goal, we collected collision detection time for both our predicted trajectory model and the traditional straight projection model. From the graph below, our method outcompetes the traditional straight model with less collision detection time. Besides the outlier of test 1, where the pedestrian was immediately detected once he entered the turn, all collision detection time of our model were roughly consistent. The traditional model, however, has a collision detection time scaling up with how far the pedestrian is down the turn, which could be dangerous to the pedestrian.
In this class, we learned how all the different parts of an autonomous system come together to form the final product, as well as a few specifics in each area to facilitate further exploration. The most exciting parts of the class were the MPs, as they always had very clear applications, and each gave you a better picture of how each part of an autonomous system works. These experiences with the MPs, as well as the concepts of how everything works together, helped us to succeed in this project by providing us a strong background to then try out new ideas.